This is your presenter, Asloob Mudassar, and I am presenting slide number 13B of the course on atomic and molecular physics. Today I shall be covering the following topics: ordinary or normal Zeeman effect, its classical theory, its vector model, splitting of states under normal or ordinary Zeeman effect. And this lecture is in continuation of the previous lecture, which was presented in slide number 13A. The Zeeman effect was reported in the year 1896. It deals with the splitting of energy terms of an atom when it is placed in a magnetic field. So the splitting of energy terms of the atoms in a magnetic field was observed in the year 1896, being a weak effect. Spectral apparatus of very high resolution was required at that time. So let me explain through this diagram the Zeeman effect. And here it is referred to as the normal Zeeman effect or the ordinary Zeeman effect. You can see that here is a sodium vapor lamp from which the light is coming, and it passes through the slit so that some of the components can be filtered out and a beam is generated. This beam, you see, that will illuminate the screen. And in the path of the beam from the source to the screen, we have placed a sodium lamp. And the sodium lamp is placed under the application of a magnetic field using magnetic pieces. Two magnet pieces are used in order to apply the constant magnetic field across the sodium flame. Now you see that the sodium atoms in the sodium flame will absorb the light from the sodium vapor lamp. Sodium atoms in the sodium flame will absorb the light from the sodium vapor because these levels, that is the sodium levels, are in resonant with the sodium light from the sodium vapor. So this light will be absorbed by the sodium atoms in the sodium flame and will be re-emitted in other directions. That is, in all other directions, the light from absorbed by the sodium flame by the sodium atoms in the sodium flame will be re-emitted in all directions, and almost no light will reach on the screen because the light has been absorbed by the flame on the way. And you can see that the shadow is a black shadow of the flame, representing that the light has been absorbed by the flame. So the light is not reaching the screen. And you can see an opaque or dark shadow of the flame. This is because the sodium in the flame, the sodium atoms in the flame have absorbed the sodium light from the sodium vapor lamp, and this light has been absorbed and re-emitted by this flame in all other directions. And almost no light is reaching to the screen which was absorbed by the flame. So that's why we see a black shadow at the screen, black shadow of the flame. Now you see that if we switch on the magnetic field using these two magnet pieces, what will happen? These magnet pieces will apply a constant magnetic field to the atoms, to the sodium atoms in the flame. And then what will happen? The energy levels are shifted. That is the energy levels in the that is the energy levels in the sodium of that is the energy levels in the sodium atom of the sodium flame are shifted. That is, the energy levels are changed by the application of the magnetic field. Due to this change of energy levels in the sodium of the sodium flame, there is a mismatch, and the sodium flame would and the sodium atoms in the sodium flame will not be able to absorb the light from the sodium vapor lamp, and this flame will appear as a transparent region. So the light from the sodium vapor flame will reach the screen, and the screen will be completely illuminated. That is, will be completely yellow, because the sodium flame on the way has not absorbed the light, because the energy levels in this sodium contained in the sodium flame has changed due to the application of the magnetic field. And now the sodium atoms in the sodium flame are not in resonant with the light from the sodium vapor. So that light from the sodium vapor is not absorbed by the sodium flame, and the sodium flame will behave as a transparent region. So the light from the sodium vapor will reach to the screen and will illuminate the screen with a complete yellow illumination. So this is what the Zeeman effect. So this experiment explains that with the application of the applied magnetic field to the atoms of the sodium, to the sodium atoms, the levels in the sodium atoms are slightly modified, and they are not the same as they were before in the absence of the magnetic field. This modification has led the light passing through the sodium flame not to be absorbed by the sodium atoms. So this light will pass as if the flame is not there, and the flame will act as a transparent region, and the light from the sodium vapor and the light from the sodium lamp will pass through onto the screen, and the screen will be completely yellow screen in the presence of the magnetic field. And again, if you remove the magnets, you will see again the black shadow, which means that in the absence of the magnetic field, the sodium atoms in the sodium flame are in resonance with the light from the sodium vapor lamp. So that light will then be absorbed by the flame, and you would see there will be a shadow of the black shadow on the screen of the flame, because the light absorbed by the flame will be re-emitted in some other directions, and a very small amount which is insignificant will be reaching to the region indicated by the shadow of the flame. So the conclusion is that application of the magnetic field will change the splitting of the levels in an atom. This is called the Zeeman effect, and here it is referred to as the normal Zeeman effect or the ordinary Zeeman effect. There is another version of the Zeeman effect which is called the anomalous Zeeman effect, and that effect will be presented in the next lecture. So you see that in order to observe, since with the application of the magnetic field, the splitting between the levels is slightly modified. So a very high resolution grating is required in order to measure such a splitting. So one option is that grating spectrometer with a long focal length and a high spatial frequency grating is required. The second option is that Fabry-Pérot interferometers could be used as a spectrometer for the measurement of the splitting due to the application of the magnetic field. So at that time when this experiment was done, so it was a problem to have a very high resolution grating, to have a very high resolution spectrometer, and then the grating spectrometer was used at that time. But now in the today's world, there is no problem, because very high resolution spectrometers are available now for the measurement of such splittings under the application of the magnetic field. So the things that I have explained in connection with the previous experimental setup, I am now going to explain them through paragraphs. A colored frame of sodium or the sodium chloride appears dark when projected using light from a sodium vapor lamp. In the presence of magnetic field, the shadow turns bright. Resonance between the light from the lamp and the light from the sodium is destroyed by the Zeeman effect. That is destroyed by the application of the magnetic field. That is the resolution, that is the resonance between the atoms of the sodium flame with respect to the sodium light from the sodium vapor lamp, that resonance is destroyed by the application of the constant magnetic field. So we can say that the resonance is destroyed by the Zeeman effect, and the flame will behave as a transparent region, and the light from the sodium vapor lamp will fully contribute at the screen, and no shadow will be recorded. Now, in the absence of the magnetic field, that is when the magnetic field is zero, there is a resonance between the light from the sodium vapor lamp and the light from the sodium flame. The sodium atom in the sodium flame absorbs light from the sodium vapor lamp, and due to the resonance emit the same light in all directions, out of which a small amount of light may reach the screen, creating an opaque shadow of the sodium flame. When the magnetic field is switched to on state, that is when the magnetic field is not equal to zero and it has some finite value, the energy levels in the sodium, in the sodium flame are shifted slightly, and the resonance is destroyed. Sodium in the sodium flame does not absorb light from the sodium vapor lamp and act as a transparent medium. The light thus reaches as brightness on the screen. Quantitative measurement of splitting is possible either number one through high resolution Fabry-Perot interferometer or by using high resolution grating based interferometers. So two types of options are available. That is, we can use either high resolution Fabry-Perot interferometer or we can use high grating based spectrometers to measure the quantitative change in splittings of the sodium levels under the application of the applied magnetic field. So splitting behavior in moderate magnetic field is shown over here. And here we are using the ordinary Zeeman effect for atomic cadmium line at lambda is equal to 6438 angstrom. So you see that this is the spectrum that we are showing was recorded with using atomic cadmium atoms. So here you see that there is one line in the absorption. This is the absorption spectrometer. That's why you see a black line over there, because the line is missing. Or you see that in other words, you can perform the previous experiments, for example, this experiment, not with the sodium lamp, but with the cadmium lamp. You can have the cadmium flame and you can have the cadmium vapor lamp, and you perform the same experiments. And you know that in the absorption, when the absorption will occur under the application of the magnetic field, you will see a black spot over there. You can perform these experiments both in absorption and in emission. That is both absorption spectrum and the emission spectrum we used to measure the spectrum. So you see that when the magnetic field is zero, you can see a black line over there. That is, there is no splitting. And you see that when you apply the magnetic field, what will happen? You can see that there are three polarized lights. The center light, which is unshifted light, is now linearly polarized with its electric field parallel to the B naught. That is, the electric field of this linearly polarized beam has an electric field which is parallel to the applied magnetic field. And there are two additional components due to, and this is the transverse observation. Transverse observation means that we are measuring this observations is made in a direction perpendicular to the direction of the applied magnetic field. So under this transverse observation, you will see three linearly polarized light. One in the center light, which is unshifted light, but now it is a polarized light, and it has an electric field which is parallel to the applied magnetic field B naught. And there are, in addition to that one, there are two other components. They are again polarized, but now in their polarization, the polarization states is such that their electric field is now perpendicular to the magnetic field B naught. So the two polarized components, why two polarized components? If they have the same electric field, that is the electric field is perpendicular to B naught, but you see that they have different frequencies. So the frequency of this component is different from the frequency of this component. That is, the energy of this component is different from this component, but the central component remains unshifted. It is the same component which could be observed when the magnetic field was not there. That is, when the magnetic field was zero, you could observe a single component there. And this single component corresponds to a wavelength of 6,438 angstrom. Now, if you apply the magnetic field, there are two ways to carry out the measurement. One is the transverse observation, that is, you observe your data in a direction perpendicular to the direction of the applied magnetic field. And the second option is that you carry out your observations in a longitudinal direction, or this is called a longitudinal observation, that is observation in the direction parallel to the direction of the magnetic field. So you see that in the transverse direction, you will see three polarized lights, linearly polarized lights. One is the unshifted light, which was the same as when the magnetic field was not present, as you see in the above case. So, but you know that here this is the same wavelength, unshifted wavelength, but now this is a linearly polarized light, and it has an electric field which is parallel to the applied magnetic field B naught. And in addition to that one, in the transverse observation, two additional linearly polarized components are also seen. But there the electric field in those polarized lights are perpendicular to the applied magnetic field. And of course, their wavelengths or their frequencies are also shifted from the central frequency. So one component on the right hand side may be assumed to have a frequency greater than that of the central wavelength, and the other component on the left will have a frequency smaller than that of the central reference wavelength. So you see that these are three linear polarized lights, and one of them, which is the central one, has the same wavelength as lambda is equal to 6,438 angstrom, but the other two wavelengths have different wavelengths, and these are three linearly polarized lights. And this observation is under the transverse observation, that is, the observation is made in a direction perpendicular to the direction of the magnetic field. Now you see that we consider another observation in which the central component is not present. So this is the same case when the magnetic field is applied, but now the observation is longitudinal. That is, we are observing the data in the direction of the magnetic field. And you know that we observe two polarized lights, but these are not linearly polarized but circularly polarized lights. In circularly polarized lights, the electric field is rotated continuously. The electric field is always perpendicular to B naught in both cases, because one of the component is a right circularly polarized light, whereas the other component will be left circularly polarized light. Which means that if you view that light coming to your eyes, one of the electric field will be rotating a clockwise, and the other component will be rotating a counterclockwise. That's why these components are referred to as respectively by right circularly polarized and left circularly polarized. So when you view these components coming towards your eyes, the electric field in those components will always be perpendicular to the magnetic field, but one always perpendicular to the applied magnetic field. But in one component, the electric field is rotating clockwise. In the other component, the electric field is rotating counterclockwise. That's why these are called right circularly polarized and left circularly polarized light. And this observation, you know that central component here is absent. And again, you have these two components, right circularly polarized and left circularly polarized. In both these components, the electric field is perpendicular to the direction of the magnetic field B naught, and in both cases, the electric field is rotating. In one case, where the light is, for example, right circularly polarized light, the electric field is rotating clockwise, whereas in the other case, where the light is left circularly polarized, for example, the light may be rotating counterclockwise. So you see that these are the observations under the application of the applied magnetic field. So you can see when there is no magnetic field, only one component is absorbed. When the magnetic field is applied, then it depends upon your point of observation. If you are observing your data in the transverse direction, that is a transfer to the direction of the applied magnetic field, then of course you will measure three linearly polarized components. One component has the same wavelength as that in the absence of the magnetic field B naught, whereas the other two components have different wavelengths. In all these components, the lights are linearly polarized, but in one component the electric field is parallel to B naught, and in other two components the electric field is perpendicular to B naught. And if you carry out the measurement of the same setup but longitudinally, you will observe two components, not the three, but only two components. One component will be right circularly polarized beam, the other component will be left circularly polarized beam. In both components, the electric fields are perpendicular to the magnetic field, but these electric fields are not constant in direction. Their direction will change and rotate as the light approaches you. One will rotate clockwise, the other will rotate counterclockwise. In the transverse observation, original line and two symmetrically shifted components are seen, as explained in the middle portion of the diagram. Under longitudinal observations, only the split lines are seen. So you see that in the lower diagram, you can see that the original or the central component is absent, whereas only split lines could be seen, which are circularly polarized. Splitting of cadmium line is called ordinary Zeeman effect or normal Zeeman effect. In transverse observation, lambda is perpendicular in the transverse observation, where the observation axes are perpendicular to the applied magnetic field direction. One unshifted and two symmetrically split components, each linearly polarized light, are observed, as shown in this diagram in the middle. In a longitudinal observation, that is in an observation parallel to the direction of the magnetic field, only two shifted components, each circularly polarized light, are observed, as you can see in the lower portion of this diagram. Now you see that here I am going to demonstrate through an experimental setup the observation axis, the applied magnetic field. So you see that this is the coil of electromagnet coil, which generates and which magnetizes this experimental setup. So due to that one, a magnetic field appears in this region, and here the sample is placed. The sample is placed over here, and the magnetic field due to this electromagnet is applied to this in the direction, in the vertical direction. So the magnetic field is applied in the vertical direction. So the direction of the magnetic field is the same as the direction of this red arrow, which is shown in the space between these two electromagnets. And you see that there are two slits represented by capital S. This is slit 1 in a transverse observation direction, and there is another slit S in the longitudinal observation. Because in the longitudinal observation, the direction of the magnetic field is the same in this vertical direction. Because the direction of the magnetic field is vertical, that's why it becomes the longitudinal observation. If you observe the light from here, but if you observe the light from here in this direction, which is the direction transverse to the magnetic field, because the magnetic field is in this direction, and here this is the direction, this is the transverse observation direction, where you are observing the components in a direction perpendicular to the direction of the magnetic field. So what will happen here? You see that I have shown in the center, I have shown three components over here. One is a red component, which is a linearly polarized light. The other two are green components, which are circularly polarized light. These circularly polarized lights will appear to be linearly polarized light when an observation is made in the transverse direction. So you see that here from the transverse observation, you will see, if you see the sample from this direction using a spectrometer, you will see that there are three components observed. One is component where the electric field is perpendicular to magnetic field B naught, and the other component, the other two are also linearly polarized, because these two green components will appear to be linearly polarized light from the transverse observation direction, where the electric field is parallel to B naught. So here we have three components which are shown over here. One component is in the center, where the electric field is parallel to B naught, which is shown also by the red arrow in the space between the two components of the magnet. So this red arrow is actually the electric field, which has electric field parallel to the magnetic field B naught. So E is parallel to B naught. This is the red component in the center, and the other two red components are actually linearly polarized lights, which is these green circularly polarized lights will appear as linearly polarized lights from the transverse observation direction, but here these are the linearly polarized, in which the electric field is perpendicular to the direction of P naught. That is why I have drawn these electric fields, these linearly polarized lights in a direction perpendicular to the direction of the magnetic field, because the direction of the magnetic field is over here in this direction, in the vertical direction. Okay, now if the observation is made of this sample using spectrometer from the longitudinal direction, that is from this direction, you will see two circularly polarized beam. One is right circularly polarized, the other is left circularly polarized. In both these, the electric field is perpendicular to the direction of the magnetic field. But you know that both electric fields are now rotating. One will rotate clockwise, the other will rotate counterclockwise, but the electric field remains perpendicular to the direction of the magnetic field. This is the longitudinal observation. So you see that this is there. Here we place the sample, and from this direction we see the sample using the spectrometer, which is the transverse direction, and from here we see the sample from the longitudinal observations, and I have explained these observations in this setup. And you know that if you switch off the magnetic field, what will happen? Only the component which is the central component over here with the electric field parallel to B naught, only this component will be observed, can be observed. The other two linearly polarized light and these circularly polarized light in the longitudinal observation, these will not be observed when the magnetic field is switched to zero state. So it means that when the magnetic field applied, splitting of the levels in an atom will occur, and due to that splitting, of course, additional energy states will be seen. So this is the setup for observation of transverse and longitudinal spectral lines in a magnetic field. Three electrons used in classical description of the Zeeman effect are indicated orbits with the arrow in the pole cap of the magnet. Emission of light source in a magnetic field can be observed in longitudinal and transverse directions. And you know that I have shown these two circularly polarized arrows, green arrows, two green arrows in with opposite senses, and one red arrows indicating linearly polarized. So you see that these may be treated, that is the electron may be treated to have three components in the classical picture. We shall in the next few pages I shall be presenting the classical description of the Zeeman effect, where these things will be more clarified. So you see that here I am going to show you the D1 and the D2 line from the sodium vapor lamp. So under normal Zeeman effect, the D1 line is split into four components. You see that I have shown D1 as a single line, D2 as a single line when the magnetic field is zero. But when the magnetic field is not zero, that is, you have applied the magnetic field to the sodium atoms, then you see that what will happen. You can see that the D line will split into four components. This is due to Zeeman effect, normal Zeeman effect, or the ordinary Zeeman effect. And this D2 line will split into six components. This will be due to anomalous Zeeman effect. And this anomalous Zeeman effect will be explained in the next lecture. So here in the today's lecture, I am talking about T1 only with the four components, which is called the normal or the ordinary Zeeman effect. And this the splitting of D2 into six components will be referred to as the anomalous Zeeman effect, and this will be explained in the next lecture. So you see that again here, the picture is that if you apply the magnetic field, further splitting will occur of the D1 lines and the D2 lines. And in the D1 lines, you can observe four different wavelengths. And for the D2 lines, there will be six transitions. So you can observe six different wavelengths. The splitting of sodium D lines is shown. It is typical of the anomalous Zeeman effect. These six lines are due to anomalous Zeeman effect, and these four lines of the D1 component are due to normal Zeeman effect. The number of components into which the lines are split is greater than those in the normal Zeeman effect. You see that in the anomalous Zeeman effect, you can see that the number of components are greater in comparison with the with the number of components yeah, of the ordinary Zeeman effect due to for the case of D1. So in the anomalous Zeeman effect, you have more components as compared with the normal Zeeman effect, and the anomalous Zeeman effect will be explained in the next lecture. Demonstration of the anomalous Zeeman effect using the sodium D lines. D1 is equal to 5,896 angstrom splits into four components, and D2, which is 5,889 angstrom, this D2 wavelength will split into six components when B naught is sufficiently large. So you see that here we are assuming for the case of for the case of Zeeman effect, we are assuming that the magnetic field we are applying is moderate. So this effect can be observed under moderate magnetic field. But when B naught is sufficiently large, ordinary and anomalous Zeeman effects merge to the so-called push-back effect. So the push-back effect could be observed under the condition that the magnetic field is sufficiently large. And the ordinary and the anomalous Zeeman effect will merge together to give you the push-back effect. This push-back effect will be explained in the not in the next lecture, but in the next lecture will be explained. So let us discuss the influence of the magnetic fields on the spectral lines and the energy terms of the atoms in the normal and in the anomalous Zeeman effect, and also in the push-back effect. So you see that this series of lectures, which will be covered under series 13, normal Zeeman effect or the ordinary Zeeman effect will be explained, for example, as in the today's lecture. Anomalous Zeeman effect will be explained in the next lecture, and the push-back effect will be explained in the next lectures. Zeeman effect and the classical electron theory. So you see that here we are going to present the techniques which was used using classical electron theory to explain the Zeeman effect. In ordinary Zeeman effect, which is we abbreviate as OZE, splitting of states involve pure orbital angular momentum. So the atoms which have pure orbital magnetism, we observe the ordinary or the normal Zeeman effect. The condition is that we have the case of pure orbital magnetism. That is, we have orbital angular momentum, we have the pure orbital magnetic moment, and the spin case and the spin things are absent. But in anomalous Zeeman effect, which we abbreviate A as AZE, splitting of states involve both orbital and spin magnetism. So both when an atom has both magnetism, that is the orbital magnetism and the spin magnetism, then we can observe the anomalous Zeeman effect. And you know that when I say orbital magnetism, it means that I am talking about three quantities: orbital angular momentum, orbital magnetic moment, orbital quantum number. And when I am talking about the spin magnetism, it means that I am talking about the three quantities, that is the spin angular momentum, spin magnetic moment, and spin quantum number. So you see that this here I have explained the difference between the two. For the ordinary Zeeman effect, the atoms should have only pure orbital magnetism. But to observe the anomalous Zeeman effect, the atoms of the atoms in the sample are required to have both orbital and spin magnetisms. Ordinary Zeeman effect OZE is described using a classical electron theory presented by the Lorentz, which we are also want to reproduce over here. In classical physics, a radiating electron is treated as a linear oscillator with a random orientation with respect to the magnetic lines of force. So you see that if you have an electron which is moving in an applied magnetic field, then you see that that electron will radiate and as a linear and will act as a linear oscillator with its direction randomly oriented in the magnetic lines of force. What force does a magnetic field exert on a radiating electron? This is the Lorentz force, which I shall be explaining in the next pages. Consider the projection of motion in a certain direction. So you see that when an electron, being a linear oscillator, is oscillating in the applied magnetic field, we can resolve the motion of that of that linear oscillator of the electrons into components perpendicular to the direction of the magnetic field and along the direction of the magnetic field, as we usually do with vectors. That is, if you have a vector, for example, in the xy plane, you can resolve the components of the vector in the along the x-axis and along the y-axis. Similarly, here we have an electron oscillator, linear oscillator placed in the magnetic field, and then that oscillator can have its oscillations along the direction of the magnetic field and also along the direction of the perpendicular to the magnetic field. So electron oscillations are replaced by three component oscillators according to the vector addition rules. And the three components mean one component will be along the b direction, the other two components will be perpendicular to the b direction. But those two components will be circularly polarized. And you know that if you add two circularly polarized components, you will get one component which will be linearly polarized. For example, if you have these two circularly polarized beams, if you could be able to combine these two circularly polarized beams along a single axis, you can produce one linearly polarized component. So that is why we have three components over here. Three components mean one linearly polarized component along the B direction, and the other two components which are circularly polarized components, they are along a direction perpendicular to B naught, and those two circular components can be thought to be added as a single linearly polarized component having electric field perpendicular to B naught. So electron oscillations are replaced by three component oscillators according to the vector addition model rules. Component oscillator 1 oscillates linearly with its electric field parallel to B naught. Oscillators 2 and 3 oscillate linearly in opposite senses, that is, they are circularly polarized light, that is right circularly polarized and left circularly polarized lights in a plane perpendicular to B naught. That is, the electric field is located on a plane perpendicular to B naught. A linear oscillator is equal to the addition of two counter rotating circular motions. So you see that the two circular motions which we say that have electric field perpendicular to B naught, you can add those two components, two circularly polarized components, to get one linearly polarized component. So if the magnetic field is zero, then you see that we can say that the oscillation frequency of the component 1 will be the same as the oscillation frequency of component 2 will be the same as the oscillation frequency of component 3, and all these will have the same frequency equal to omega naught. So when the magnetic field is not present, and if you try to resolve the magnetic, if you try to resolve the electron as a linear oscillator along the hypothetical B naught direction, because B naught is not present, but if you resolve those, if you resolve a linear electron oscillator along the hypothetical B naught direction and perpendicular to the hypothetical B naught direction, that is, you have three components, then all these three components will have the same frequency omega naught. And you know that when B naught is not present, then of course these component, that is the oscillation frequency of component 2 and oscillation frequency of component 3 will be hypothetical components. Now what will be the forces on the three components under the application of the magnetic field? Component oscillator 1 oscillates linearly with the electric field parallel to B naught, because the force on that component will be equal to 0. You know that in the Lorentz force field, we have the component which is called a V cross B component, where V is the velocity of the electron oscillations. And you know that when the electron oscillates along the direction of B naught, then V cross B will be equal to 0. That's why the applied force, that is the Lorentz force due to the magnetic field, will be equal to 0 on that component which has electric field parallel to the direction of B naught. So the component oscillator 1 oscillates linearly with its electric field parallel to B naught and will be subjected to zero magnetic force. Now the frequency of oscillation remains unchanged. So you see that when there is no force on that component, so the force will not change. The force, since the force is zero, no modifications will be done to that component. So that component will remain unchanged. So the linearly polarized light is emitted with electric field parallel to B naught. Now you see that in the diagram over here, let me read the caption of this diagram. Classical explanation of the Zeeman effect. An oscillating electron is resolved into three component oscillators. You see that I have shown the direction of the magnetic field B naught along the Z direction. And you see that this electron represented with green e to the power minus e, this is the electron, it is oscillating along this diagonal direction. So this is the direction of oscillation of the electron. And with respect to the magnetic field, we can resolve this component of the oscillations into two directions. One parallel to the direction of the magnetic field, which is represented, which is labeled by 1 and shown by the dotted lines parallel to the direction of the magnetic field B1. This is the one component we have resolved, and there is another component which is perpendicular to the oscillation, which is perpendicular to the direction of the magnetic field. And this is again a linear component. So the component 1 is linear, and the component perpendicular to B naught is also a linearly polarized light, which can be viewed as component 2 and 3. One is right circularly polarized and the other is left circularly polarized, because these two right and left circularly polarized lights have electric field perpendicular to the direction of the magnetic field B naught, and if you could combine these two components together, you could be able to produce one linearly polarized component with its electric field perpendicular to the direction of the magnetic field B naught. So the oscillations of the electric field with any direction, in any direction to the direction of the magnetic field B, can be resolved into two components, one along the B naught direction, the other two are along the are perpendicular to the B naught direction, as right circularly polarized and left circularly polarized. And you know that if you carry out the observation from the x direction or from the y direction, these observations will be transverse directions. But if you try to carry out the observations from the z direction, then this direction will be longitudinal direction. So from the longitudinal direction point of view, you would be able to see only component 2 and 3. if you view if you view the field from the z direction, but if you view the field either from the x direction or from the y direction, which are the transverse directions, you will see the three components, three linearly polarized components. One component will have its electric field parallel to the direction of the magnetic field. The other two shifted components, which are also linearly polarized when viewed from the x or y direction, will be linearly polarized beam with its electric field perpendicular to the direction of the magnetic field. As I have explained in this direction, in this diagram, and also okay, and also in this diagram, and also particularly in this diagram. Okay, now we want to calculate the shift of these components. So you see that under the application, when these components will shift, for example, as I have shown you the shifting of the components over here, and if you have other components, for example, the components where these two components linearly polarized components, which are the shifted components, and similarly these two circularly polarized components, which are the shifted components. Now the question is that what is delta omega of these components? That is, how much are they shifted with are they shifted in frequency with respect to the unshifted components? So we want to calculate the shift, we want to calculate the shift delta omega for these components. Components 2 and 3 are either accelerated or slowed down by the effect of the magnetic induction when B naught is turned on. The circular frequencies are increased or decreased by an amount delta omega equal to half times E over M naught times B naught, because this has been measured and was found to be equal to this quantity. So multiplying with H bar and dividing by H bar, you can introduce Bohr magneton mu B. So mu B over H bar is times B naught. So this is the delta omega. This is the shift in frequencies of the two components with respect to the central component. You know that the central component, when we apply the magnetic field, the angular, if only it is the case of a pure orbital magnetism, the angular momentum as well as the magnetic moment, orbital magnetic moment of the electron, they starts their precessional motion about the magnetic field B naught. And this frequency and the precessional or the angular frequency of those components is referred to as the Larmor frequency, which we have also discussed in the previous lecture. And now it is omega L is equal to GL times mu B over H bar into B naught. So you can connect, you can see the similarity of this omega L compared with the shift in frequency as given in equation number 12. So you can compare equation number 12 and 13, and you will see that these the Larmor free, that is the shift in those components is of the order of the Larmor frequency omega L, provided you set GL is equal to 1. And you see that we have seen in the previous lecture that the value of GL for the case of the pure orbital magnetism is equal to 1. So GL will be equal to 1. And you know that when only spin magnetism was present, the expression corresponding to the Larmor frequency was equal to Gs into mu b over h bar into b naught. But here we are not concerned with the equation number 14. I have just reproduced this equation so that you can make a comparison of the frequency of precessional frequency of the orbital angular momentum and the precessional frequency when the spin resonance is present over there. That is the spin, that is the case of a pure spin angular pure spin magnetism was present. So equation number 13 is the case when pure orbital angular orbital magnetism is present, and equation number 14 is the case when pure spin magnetism is present. But here we are not concerned with equation number 14. Just make a comparison of equation number 12 and equation number 13. And in the previous lecture, we have also observed that GL has a value equal to 1. So if you put GL is equal to 1, you can see that the precessional motion of the angular momentum of the electron about the applied magnetic field B naught is equal to the change in shift of the frequency of the components, of the other two components, which are the shifted components. So equation number 13.12 is different from equation number 14 by a factor of Gs is equal to 2. So you see that ignore this statement and also equation number 14 because they may confuse you. So move ahead. Here we are dealing with the orbital magnetic moment or orbital angular momentum for which the value of GL is equal to 1 instead of the spin magnetism for which the GS value is equal to 2. So consider only GL is equal to 1 because here we are considering pure orbital magnetism. And under that condition, you can see that the precessional motion of the orbital angular momentum or the spin or the orbital magnetic moment of the electron around the magnetic field is the same as that of the shift in the frequencies of those shifted components. So when B naught is equal to 0, the electron circular frequency is omega naught. The Coulomb and the centrifugal force balance each other. You know that when an electron is revolving around the nucleus with a radius r, you can write down equation number 15 immediately. On the right hand side, we have the Coulomb force. On the left hand side, we have the centrifugal force. So we can put this negative sign either on the left hand side or on the right hand side. This Coulomb force is actually the attractive force, and this force on the left hand side is the centrifugal force, which is the repulsive force. These two forces will have the same magnitude but opposite in directions as shown in equation number 15. So this is the vectorial form of the equation for an electron or for an orbit of the electron where the two forces balance each other. Let a homogeneous magnetic field B naught is applied in the z direction. The Lorentz force is now given by the Lorentz force F will be equal to the Coulomb force, that is the force due to charges, plus the forces due to the presence of the magnetic field, which is a plus Q into V cross B, where V is the motion of the where is the velocity of the motion of the charge under the in the magnetic field, and you know that is this is the cross product. So this F Coulomb force, this is the Coulomb force can be replaced by minus times the centrifugal force, and this Q charge can be replaced by minus E because minus E is the charge on the electron, and we can represent the velocity V as R dot because R dot is the first derivative of R with respect to time, which is the velocity. So this is from equation number 15, I have substituted the value of centrifugal force equal to minus m omega naught square into vector r. And on the left hand side, I have represented this force as mass times acceleration. Now I can represent this force into components form. You can see that the acceleration has been written as x double dot into unit vector I plus y double dot into unit vector j plus z double dot into unit vector k, where x double dot represents the double derivative of x with respect to time. Similarly for the other components. And here the middle term is minus m into omega naught square, and r represented by x into unit vector I plus y into unit vector j plus z into unit vector k. And r dot cross b has been represented in the form of determinant, where the first row is the unit vectors I, j, k. The second rows are the components of the r dot, where we have the components of r dot as x dot, y dot, and z dot. And b has only one component along the z direction. The other two components along the x and y direction are zero. So we have 0, 0, and b naught. So you see that if you equate the I components, Z component, and I component, Y component, and Z components on both sides of this equation, you ultimately get these three equations. That is equation number 16, 17, and 18 can be obtained by comparing the coefficients of I unit vector, y j unit vector, and z unit vector on the two sides, and we can immediately write these three differential equations. Now, if you talk about the solution of component 1, which is the easiest component, you can immediately write its solution to be of the form of this, that is z is equal to z naught into e to the power iota omega naught t. That is, this component is oscillating with the central frequency omega naught. And you know that omega naught is also the central frequency when the magnetic field is zero. And you can notice in equation number 18 that magnetic field is not present in this expression. In equation number 18, magnetic field B naught is not present. That is, the frequency of oscillation in the z direction remains unchanged, equal to omega naught. Now you see that we can solve the differential equations shown in equation number 16 and 17, in which the magnetic field B naught is present. To solve equation number 16 and 17, the following substitutions are used. U is equal to x plus iota y, and v is equal to x minus iota y. Or you can say that x is equal to u plus v over 2, and y is equal to u minus v over 2 iota. So if you make these two substitutions in the previous differential equations, that is equation number 16 and 17, and solve them simultaneously under the condition that E b naught over 2m is less than b naught. That is, you choose the moderate value of the magnetic field so that this inequality holds, then you can write down these two solutions, because these two solutions have been obtained under this approximation, under these assumptions. And you have the two solutions, u is equal to u naught into e to the power iota times, within the parentheses we have omega naught minus e b naught over 2m, and outside the parentheses we have time factor. Similarly, for the component v, we have v is equal to v naught e to the power iota. Within the parentheses, we have omega naught plus e b naught over 2m, and this is in the parentheses. Outside that one, we have the factor t. So equation number 22 and equation number 23 are the solutions of the equation number 16 and 17. You can also, if you want, you can also solve, you can substitute these values in equation number 21, and you can solve your equations in terms of the parameter x and y. You see that if you look at the coefficients of e to the power iota, you will see that e b naught over 2m is present in both these solutions. So this is actually delta omega. So delta omega is equal to e b naught over 2m. You know that we have omega naught over here in both the equations. We have also these parameter e b naught over 2m, which we represent as delta omega. So the first solution can be read as omega naught minus delta omega, and the second solution can be read as omega naught plus delta omega. So this delta omega is actually E b naught over 2m. And you know that this delta omega is the same thing as we have introduced previously over here, because you can introduce h bar on the numerator and the denominator, and you can represent that delta bar also in the form of Bohr magneton divided by h bar, and then multiplying this factor with b naught, which is also equal to the Larmor frequency. These are the equations for the left hand and the right hand circularly polarized or circular motions with frequencies equal to omega naught plus minus delta omega. That is one of the component which we may label as a right circularly polarized component will have a frequency which is greater than the normal frequency given by omega naught plus delta omega, and the other will have the reduced, the other component will have a smaller frequency represented given as omega naught minus delta omega, and which we may name as left circularly polarized light. The component electron oscillators 2 and 3 thus emit or absorb circularly polarized light with the frequencies is equal to omega naught plus delta plus minus delta omega. The model correctly predicts the splitting of ordinary Zeeman effect. So you see that from the classical model, we have seen that the delta omega that we have measured over here is equal to the Larmor frequency. And it is also equal to the frequency with which the other two components have shifted with respect to the central components. And the classical model has explained well the splitting of the ordinary Zeeman effect. And you can also solve this equation for the value of linear frequency delta nu, which is equal to delta omega over 2 pi and is equal to 1 over 4 pi into EB naught over M naught. And if you substitute the values of charge, the magnetic field B naught equal to 1 Tesla, M naught is the mass of the electron, you will find out this expression equal to 0.465 centimeter inverse or 1.4 into 10 to the power 10 hertz or second inverse. And this expression was obtained using B naught equal to 1 Tesla. So delta nu is the same for each spectral value for a given B naught and is independent of the value of nu. And you know that this delta nu corresponds to those components which are the shifted components, because the shifted components depend on the value of B naught. Prediction about polarization of Zeeman components. Component electron oscillator 1 oscillates in a direction parallel to B naught. That is, this component which is linearly polarized and is the central component having frequency omega naught is the component in which the electric field is parallel to B naught. Oscillations have characteristics of a Hertzian dipole oscillator. You know that in the Hertzian dipole oscillator, what happens is that the emissions takes place in all directions in the form of spheres. Similarly, with this is also a this is also a form of Hertzian dipole oscillator in which the oscillations can be measured in all directions. Intensity of the radiation is 0 in the B naught direction. This is in agreement with the unshifted Zeeman component. It is called the pi component, pi for parallel. So the component in which the electric field is parallel to the magnetic field is called the pi component. And you can see that in this diagram, the pi component is the component with the electric field parallel to B naught. So this is the pi component, electric field parallel to B naught. And you know that this component is not present over here in the longitudinal observations, because in these longitudinal observations and in the two observations in which the electric field is perpendicular to B naught, these are not the pi components, because the electric field is perpendicular to B naught. These may be referred to as the sigma components. And you know that the electric field of such components with the electric field is parallel to B naught cannot be observed in the longitudinal direction, because this component in which the electric field is parallel to B naught is cannot be observed in the longitudinal direction. This is only observed in which the you measure the field in the transverse direction, where the linearly polarized field has electric field parallel to B naught. And you know that this component is referred to as the pi component. Pi stands for parallel. That is, the electric field has a direction parallel to the B naught. This is called the pi component. Now the component of electron oscillators 2 and 3, when observed parallel to B naught, that is from the longitudinal direction, oscillations have circular polarization. But when observed in a direction perpendicular to B naught, it is linearly polarized. In this case, the radiations are designated as sigma plus and sigma minus, and sigma is referred to as perpendicular direction. So the two linearly polarized components, these two linearly polarized components, in which the electric field is perpendicular to B naught and measured in the transverse direction with the electric field perpendicular to B naught, may be referred to as the sigma components. Whereas this component, linearly polarized component in the center, where the electric field is parallel to B naught, is referred to as the pi component. So we can have two sigma components, and in the middle we have the pi component. So these components may be referred to as a sigma plus component. Sigma plus component is the component in which we have the frequency as omega naught plus delta omega, and sigma minus will be the component in which the frequency will be omega naught minus delta omega. Because you see that in the previously we have shown that the components will have frequencies omega naught plus minus delta omega. Okay. Sigma plus represents a right circularly polarized light, whereas sigma minus represents left circularly polarized light. Sigma plus sign stands for increase in frequency, and sigma minus sign stands for decrease in frequency. That is, the frequency of sigma plus will be equal to omega naught plus delta omega, and the sigma minus component will have the frequency omega naught minus delta omega. Different polarization components of light are used in optical pumping to selectively populate individual Zeeman levels. So you see that if you have the sample, you apply the magnetic field, then of course you have additional splitting of those levels due to the Zeeman effect in the presence of the magnetic field. So due to we have different levels, and we have these levels which can be excited with the different lights of different polarization states. That is, you can use sigma plus light or sigma minus plus light, and pi light in order to selectively pump different levels in the Zeeman structure or in the Zeeman levels. So different levels in the Zeeman effect can be excited selectively by choosing light of different polarization states. Now description of the ordinary Zeeman effect by vector model. Here we are going to explain the vector model, Zeeman effect by the vector model, and the vector model is very much similar to the quantum mechanical treatment. Classical treatment of the ordinary Zeeman effect was presented in the previous section. Now I am presenting the treatment of the ordinary Zeeman effect using the vector model, which can be inferred from the quantum mechanical treatment also. Complete quantum mechanical treatment will be given in some other lectures. So in the presence of the applied magnetic field B naught, J, which is the total angular momentum of the atom, and mu J, which is the total magnetic moment of the atom, these two quantities, that is J and mu J, execute precessional motion about B naught. the additional energy of the atom in the presence of B naught, also known as the magnetic potential energy, is given by. So you see that if you apply magnetic field B naught to an atom, the atom acquires additional magnetic potential energy, and that additional potential magnetic field is given by VMJ, where MJ is the magnetic quantum number. J, since J stands for the total magnetic quantum number, so here Mj stands for the total magnetic quantum number. And this Vmj is due to the total magnetic quantum number of the atom. So Vmj is equal to minus the dot product of mu j with B naught. That is the dot product of the total magnetic moment of the atom with the applied magnetic field. So this is minus mu j B naught cos of alpha, and you can combine minus mu j, you can combine mu j cos of alpha, and you can represent it as z component of mu j, that is the component of mu j in the z direction, which can be represented as mu j comma z. And you know that in one of the previous lectures, we have represented the z component of mu j. We have represented mu j z, that is the z component of mu j, to be equal to gj into mu b into mu into mj. So this expression we have derived in one of the previous slides. So now our magnetic potential energy becomes equal to Vmj is equal to minus, within the parentheses we have Gj. Gj is actually the total Landé G factor. Mu B is the Bohr magneton. Mj is the total magnetic quantum number. And B naught is the applied magnetic field, where the total magnetic quantum number of the atom under the application of the magnetic field is Mj is equal to 0, plus minus 1, plus minus 2, and so on up to plus minus j. That is the maximum value that Mj can take will be equal to plus minus j. In the presence of the magnetic field B naught, the level J is split into 2J plus 1 levels. You can see over here, these Mj values are actually 2J plus 1 values. And if the magnetic field is not there, then of course Mj is equal to 0. No splitting. And when the magnetic field is 0, then there will be only one J level. So there will be only one level corresponding to one value of J. But if you apply the magnetic field, then that J level will be split into Mj levels. That is, will be split into 2J plus 1 levels. That is, there will be a splitting of the J levels. That is, the J level degeneracy is lifted. So when there is a splitting of a level, we say that the degeneracy is lifted. So in the presence of the magnetic field B naught, the 2J plus 1 fold degeneracy is lifted, and the energy term with a given J is split into 2J plus 1 components, which are equidistant in energy. And the energy difference between the components is given by delta E, which can be derived from equation number 25. We can derive this one, that delta E, which is also the energy between the two consecutive components, between any two components. Delta E is equal to Gj into mu B into delta Mj into B naught, where then delta Mj is the change in the total magnetic quantum number of the atom. And correspondingly, we have the energy, we have the change in energy, which is represented by delta E. So for two consecutive levels, delta Mj will be equal to 1. The energy difference between the two consecutive components is found by setting delta Mj is equal to 1, and that is given by equation number 27. So delta E, that is the energy difference between the two consecutive components, delta E is equal to Gj into mu B into B naught. And you know that the value of B, mu B is E h bar, E into h bar over 2 m naught, where m naught is the mass of the electron. In ordinary Zeeman effect, only the orbital magnetism is considered and the spin magnetism is ignored, for which mu j, which is the total magnetic moment of the atom, will be the same as equal to the orbital angular momentum, and the gj value, which is the total Lambda g factor, will be same and equal to the Lambda g factor due to the orbital case, which is gl, and gl has a value equal to 1. So if you substitute that Gj is equal to 1 over here, then equation number 27 can be taken to be equal to, can be taken to hold for the case of a pure orbital magnetism. So delta E, and you know that the pure orbital magnetism means that we are talking about the ordinary Zeeman effect. So delta E is equal to mu B times B naught, and you know that delta E can be represented as h bar omega, simply as h bar omega, or just to show that this omega is due to delta E, due to change in energy, we are representing it over here as delta omega. And you know that here we can write it as h bar into 2 pi and delta nu. So you can simply represent here omega only, that is h bar omega is also sufficient to represent this one, and then that omega will be equal to the difference of will be equal to the difference in energy delta E. So better to represent delta E, we have used delta omega, and also delta nu on the right hand side. So you can equate the term on the right hand side with the term mu b into b naught, and you can find delta nu is equal to mu b into b naught over h bar into 2 mu. So you can here introduce Bohr magneton, which is equal to E into h bar over 2 m naught, and the simplified result is 1 over 4 pi into E over m naught into d naught. And you know that this delta nu is the same change in the linear frequency of the shifted components. And if you represent it in the form of delta omega, it will be equal to the precessional or the Larmor frequency. And the shift in the components due to the application of the magnetic field as observed in the ordinary Zeeman effect will have a frequency equal to delta nu or delta omega. So this is the same as obtained using a classical theory, or the electron, or the theory that we have presented using Lorentz model, Lorentz electron model. And you know that here using the vectorial model, we have also obtained the same result. Now you see that I am going to take some particular examples so that I can further explain ordinary Zeeman effect. For the optical transitions, the selection rule is delta mj should either be equal to 0 or should be equal to plus minus 1. This is our selection rule. And you know that optical transition means that this selection rule is applicable where a wavelength is emitted under the transition. That is, the number of lines is always 3. So one line will correspond to delta mj is equal to 0. The other 2 lines will correspond to delta mj plus minus 1. So there will be 3 lines in the ordinary Zeeman effect. That is, the number of lines is always a 3, also called ordinary Zeeman or triplet. So this is called ordinary Zeeman triplet. This is a quantum mechanical picture as it involves the magnetic quantum number mj. Consider neutral cadmium atom, CD atom, or the cadmium atom. The cadmium atom has 48 electrons. The ground state of the cadmium atom is 5s2. And the next 2 excited states of the cadmium atom will be 5s5p and 5s5d. Now you see that we want to calculate the term associated, the spectroscopic term associated with these 2 excited states, that is 5s5p and 5s and 5d. So let's consider 5s and 5p, the first case, where the electron has a spin quantum number s1 is equal to half. The p electron has also a spin quantum number equal to half, because the spin quantum number is the same for the case of single electron, whether it is s electron or p electron. and but the orbital quantum number for the s electron is 0, and the orbital quantum number for the p electron is 1. So total s, that is the sum of quantum numbers for the spin, that is the total spin, will be equal to mod of s plus minus 1. And here I am only going to take the negative sign over here. Half minus half is equal to 0, because I want to have a case of a pure orbital magnetism. That is, I want to get rid of the spin magnetism. That's why I have used a negative sign over here, so that the spins are antiparallel to each other. That is, the spins will cancel out each other. The total spin of the atom in this excited state will be equal to 0. And also, when the total spin quantum number is 0, it means that the total spin angular, that is the spin angular momentum, will be equal to 0, and the spin magnetic moment will also be equal to 0. So there is no spin magnetism, and if you add L is equal to L1 plus minus L2, and then L1 is equal to 0, L2 is equal to 1, adding plus minus 1, you have only L is equal to 1. Capital L is equal to 1, and the capital J is equal to mod of L plus minus S. And if you add capital L is equal to 1, capital S is equal to 0, capital J will be equal to 1. And you know that you can calculate the multiplicity. The multiplicity is equal to capital M is equal to 2 times capital S plus 1, and capital S is equal to 0 in our case, so the multiplicity is equal to 1. Multiplicity tells you the number of possible values of J. So the term can be written as M with multiplicity P, and the term symbol is capital P, because capital L is equal to 1. So if the capital L is equal to 1, the term symbol will be capital P, and the capital J is the total value of the angular momentum quantum number J. So substituting these values, the term becomes equal to 5 and 1p1. So this is for the excited states, which was 5s and 5p. Now let's move on to the second excited state, which is 5s and 5d. For the s electron, we have spin quantum number s1 is equal to half. Similarly, for the d electron, the spin quantum number s2 is equal to half. So the s1 and s2 are the spin quantum numbers related to s and d electrons. Since these are electrons with a single, these are the electron states with single electron, that's why I have s1 is equal to half and s2 is equal to half. So for the s electron, I have the orbital quantum number L1 is equal to 0, and for the d electron, I have orbital quantum number L2 is equal to 2. And here capital S is equal to mod of S1 plus minus S2. Again, I am choosing a negative sign over here, that I have half minus half is equal to 0. And then you see that the spin, one of the electron will have a spin up, the other electron will have a spin 0, will have downward spin. The two spins orientations will cancel out each other, and the total spin quantum number will be equal to 0, as capital S is equal to 0 in this case, because we want to get rid of the spin magnetism. So that's why I have chosen a negative sign over here. The other is the orbital quantum number, total capital L, which is equal to mod of L1 plus L2. L1 is equal to 0, L2 is equal to 2, and so capital L is equal to 2. Similarly, the total angular momentum J of the atom is a capital J is equal to mod of L plus minus S, and then 2 plus minus 0 will equal to 2. The multiplicity will be equal to 2 times S plus 1. The capital S is equal to 0 over here, and then you see that multiplicity is equal to 1. That is, there will be one possible orientations of J with respect to the, so there will be one possible values of J. So the terms can be represented as term is equal to 5 into multiplicity 5, and then the term symbol is capital G due to the value of capital L equal to 2, and then the multiplicity is represented at the top left corner, and the capital G, that is the total quantum number J, is represented as a subscript. So substituting these values, the term is represented by 5 as 1d2. So 5 is the principal quantum number, and 1d2 is actually the term symbol of these spectroscopic terms. So I have the two, you know, that excited states, represented by 5s and 5p. The second excited state is 5s and 5d, and I have written their corresponding states as 1p1, 5, 1p1 and 5, 1d2. Okay, so now consider the transition 5 1d2 to 5 1p1. This transition will give you a wavelength of 6438 angstrom. And this transition has a wavelength which is this wavelength, and this is in the absence of the magnetic field. Now, in the presence of the magnetic field, 1d2, where J, the value of J is equal to 2, will split into 5 levels. Because when J is equal to 2, Mj will have the possible values of 0, plus minus 1, plus minus 2. So 1d2 level in the presence of the magnetic field will be split into 5 levels. Similarly, I have 1p1 with capital J is equal to 1. So it will split into 3 values because the corresponding Mj value will be equal to 0 plus minus 1. So 1d2 level will split into 5 levels and 1p1 will split into 3 levels. That is, the J degeneracy will be lifted. This J is equal to 2 level will be split into 5 Mj levels, and this J is equal to 1 level will be split into 3 levels. So these levels are shown in the presence of the magnetic field. And these have equal spacing between them. So you can see that I have shown Mg levels on the rightmost side. The central of each one has Mj is equal to 0. Then Mj is equal to plus 1 plus 2. These are the levels with greater energy, and the lower in energy are the levels with Mj is equal to minus 1 and Mj is equal to minus 2. Similarly, when we consider the splitting of 1p1 under the application of the magnetic field, we have 3 levels with Mj0 and Mj plus 1 and Mj minus 1. And you know that I have shown the transitions between these levels with the delta J, because delta J, which allow the permissible transitions, are only delta J is equal to 0 plus minus 1. So these are the allowed transitions. These are the allowed optical transitions. When delta Mj is equal to 0, we have the pi transition. When delta Mj is equal to plus minus 1, we have the sigma transitions. And you know that the pi transitions will occur with the same value of J, with the same value of Mj, so that the difference of Mj will be equal to 0 as shown for the green lines. Whereas the red lines are due to the transitions where Mj is equal to plus 1, where delta Mj is equal to plus 1. And these light brown transitions represent delta Mj is equal to minus 1. So it means that there are actually 9 transition lines, but only 3 frequencies are emitted. So due to these 3 frequencies are emitted, that is 3 components will correspond to pi component, 3 will be sigma plus component, 3 will be sigma minus component. But you know that these, for example, the pi component which have the 3 components, they have the same wavelength or the same frequency. So we cannot discriminate them. So it means that these 3 lines will be treated as a single line. Similarly, the other 2 lines, that is the sigma plus line and the sigma plus line, will also be treated as single lines having single frequencies, though different from the central frequencies. So we have shown, you know that over here we have shown 3 lines. And the delta Mj, you see that has been shown as minus 1, 0, plus 1. And correspondingly, I have 3 lines shown with an increase of a wave number. So we have sigma line, we have the pi line, and then we have the sigma minus line. You can represent them more precisely as sigma plus line for the line on the right hand side of the pi line, and sigma minus line for the light on the for the sigma line on the left to the pi line. And these are the wave numbers, which means that the sigma plus line has a frequency greater, has a wave number greater than the pi line, and the pi line and the sigma minus line, which is on to the left of the pi line, which has a frequency smaller than that of the pi line. Capital letters as term symbols. You know that we have used the term symbols capital P and capital D because this is the cadmium atom is the case in which more than one electrons are present, and we should need and we it is required that we use capital letters as the term symbols. So that's why we have used two capital letters, that is a capital P and capital D, as the term symbols for our excited states. That is a P term for the first excited state and capital T as the term symbol for the second excited states. So these have been used because the two electrons contributed in the formation of states. Now the splitting is equal in each case because only orbital magnetism is involved and the spin magnetism was absent. Now, if someone asks you why these splitting are constant, that is a separation between splitting is constant. The reason is that we are dealing only with the pure orbital magnetism case. That is, the spin magnetism is absent in this case. That's why the splitting of the levels is constant. Undisplaced lines correspond to delta mj is equal to 0. So undisplaced lines are the lines which were the lines in the absence of the magnetic field. Or if you apply the magnetic field, those lines are not shifted in their frequencies. Those lines are called unshifted lines. So the unshifted lines correspond to delta m is equal to 0. And the displaced lines correspond to delta mj is equal to plus minus 1 are circularly polarized if observed from the in the longitudinal direction, and if observed in the transverse direction they will be linearly polarized light. So you see that I have explained the ordinary Zeeman effect or the normal Zeeman effect in much greater detail. In the next slide, I shall be talking about the anomalous Zeeman effect. So this lecture is continued. But for now, this is the end of slide number 13B of the course on atomic and molecular physics.